Hello, everybody. This is Zhenjiang Shen from LinkedIn. Today, I'm going to talk about our effort on developing and improving our retrieval system for job search and job recommendation product. This is a joint effort with my awesome colleagues, Yuqing, Xiaobo, Chenqi, Caleb, Luke, Wenjing, and Yangjie. So a common challenge for the modern recommendation system is scalability. At LinkedIn, we need to connect over 80 million active job seekers with tens of millions of job opportunities. To handle this kind of scalability, we adopted the classic two-stage architecture, including both retrieval and ranking for our product. In this talk, we will focus about our effort on the retrieval systems, which can be divided into three phases. When we launched our product, we adopted the inverted index system built on top of CPU. Due to the relevance quality issues and productivity challenge, we started revising the inverted index system to support the learning to retrieve framework. This included our early effort around embedding-based retrieval, but still the challenges existed. So we developed a new exhaustive search paradigm on top of GPUs. Let's start from the very beginning, inverted index. So inverted index, they enabled fast, robust, and expandable term matching. On the hood, we have multiple taxonomies for our job product, including seniorities, titles, skills. For each taxonomy, we build an ML model and convert the job description into a list of attributes. In runtime, when your queries come in, we convert the queries into a list of attributes using those taxonomy models, and then match against the job opportunities. I'm pretty sure most people in the conference have used LinkedIn product and have complaints about relevance qualities. I apologize that on behalf of my colleagues. The reason is because the under hood taxonomies and taxonomy models, if anything is wrong, then the matching quality is completely off. I give you some examples here. One is about seniority taxonomy. Many companies, they have director roles, but their requirement for qualification are very different. If I match the director roles to you blindly, then you complain about qualification issues. Another example is about skill taxonomy. Right now, generative AI is becoming trending, but in our old skill taxonomy, we do not have generative AI. That means even if I'm expert on generative AI, we might have difficulty in matching you to the right opportunities. So all those relevance quality issues motivate us to explore the embedding-based retrieval. Like many other companies, we started by revising our inverted index system to support approximate nearness neighborhood search, specifically IVFPQ in our use cases. However, very soon we realized some challenges with these kind of incremental approaches. One challenge is around iteration velocity. We have to develop multiple intermediate components for the ANN, such as clustering essentials, quantization, code book, and so on. Those intermediate components, they do not just cause relevance degradation, they also slow down the model development cycle. In addition, if you want to run ANN online, you have to deploy those models and intermediate components to the inverted index. So everything slows down the R&D process. For the real product development, the expand velocity is actually pretty crucial. Another challenge is around model constraints. Inverted index is not designed for handling dense vectors. If you want to adopt the state-of-the-art LLM embeddings, then in inverted index, we have a lot of challenges. So very soon, we reach the conclusion, incremental change on top of inverted index system is not sufficient for this new world, and we need a fundamental infrastructure change. So our journey is a good reflection of Rich Sutton's big lesson. The great power of general purpose methods, or methods that continue to scale with increased computation, even as available computation becomes very great. So what we have done? We designed a new paradigm called exhaustive search on GPUs. In this new paradigm, we completely discarded inverted index, and the core components only boils down into three ones in GPU: a sparse matrix, a dense matrix, and a message. So the sparse matrix is used to represent items and the attributes for term-based matching, And dense matrix is used to store item embeddings, so we can do semantic matching. And the messages support the lightweight, zero-copy communication among different components and different stages. With this new design, we can support the real hybrid search for both term-based matching and semantic matching. The term-based matching are evaluated using parallelized sparse matrix operation, and embedding-based matrix, embedding-based retrieval are completed by using high-throughput dense matrix operation. There is zero approximation in our system, such as HM, SWL, or IVFPQ. So out of box, this new GPU system already demonstrates amazing performance. We further push its performance by doing the following system-level optimization. There is a lot of sorting, selection operation in retrieval phase. So we introduced a highly efficient top case selection algorithm inspired by bucket sorting. We also redesigned the messaging system, so you don't need to do unnecessary copying or reading among the data. We also adopted the BF16 precision to reduce the memory consumption and computation cost. We also customize matrix operation by considering our specific data pattern. We designed a batching strategy to balance the GPU utilization and latency requirement for our product. We partitioned the retrieval space by considering the content locality, so you don't need to do unnecessary computation and memory access. And lastly, with all those efficiency improvement, we removed all the intermediate approximation in our system. So further simplify the system and give flexibility to engineers. So you are probably curious about the system performance of this exhaustive search on GPUs. This is the benchmark result using one single A100 GPU, 4 million documents, and 3,584 dimensional embeddings. Out of box, system can do about 80 QPS on one single GPU. With all the optimization we have conducted, the system can handle about 1,200 QPS on one single GPU. So with this efficiency, we were able to deploy the GPU system to support all job seekers in US. And we've seen some amazing business impact out of this new system. On the system level, we reduced the serving cost by more than 75% compared with the legacy CPU-based inverted index system. And we also improved the expanding velocity by more than 30%. In this new system, we give engineers a lot of flexibility. They can access the attributes and embedding directly, and they can run operations beyond the dot products. So those kind of flexibility give engineers the power to do advanced modeling, such as multi-objective or multi-embeddings for retrievals. And we've seen some good business metric out of it, such as 4.6% job application lift and 5.8% revenue lift for the first model launch. So out of our journey, we have some very interesting learning lessons we want to share with everybody. First, hardware-aware design is crucial. Many assumptions we have for the CPU world, they do not translate into the GPU world. If you want to fully embrace the LLM capacity, then you have to rethink about your system design strategy for your ranking and retrieval system. Secondly, flexibility unlocks a lot of business impact. As we mentioned, this new system gives engineers a lot of flexibility. They were able to develop powerful model for retrieval system. Third one, inverted index, they have flexibility walls. As we mentioned, if you want to fully utilize LLM for your ranking and retrieval, then inverted index system is not sufficient. Lastly, paradigm shift requires full stack investment. Beyond the core info, you also need to think about tooling, monitoring, and new operation practices. With that, I think I'm ready to take questions from the audience, and thank you for your attention.
Yeah, I have a question. Let's say partitioning by country, it's not only technical decision, because on current job market where most jobs are remote, I mean significant, this decision has a serious business impact for both candidates and companies. So how you balance technical decisions with kind of these business ones?
Yeah, I think that's a good question. Fundamentally, in the GPU world, how to organize data is very important because you don't want to read some data from one place and then read another data from another places. So one of the operations we have done is to organize the data based on the frequency they will be accessed. And later on, we also identify actually if we are coming from a certain country, then we only need to show jobs from that country due to the all kinds of reasons. So in that case, we don't even need to access the data beyond a certain country. The content locality further improves system performance. So all in all, organized data and avoid unnecessary memory reading in the GPU world is crucial for the performance.
Hi, thank you for the talk. I wanted to ask, so now that you're using the GPU and kind of the memory access is quite important, how can this approach deal with dynamically updating embedding? So if you want to update, for example, user or job embeddings frequently, how can you deal with that?
Yes, essentially in our current use cases, one GPU can load at least 3 copies of the job repository. So that allows us to update the memory frequently. Whenever there is update to the job information, we can rewrite one of the data copy and then replace that with this latest copy.